in my talk, I'll basically build on what Tim told us about on Tuesday and go over molecular dynamics and what we can do with MD on exascale machines. So I won't review the basics, but I'll kind of go through a case study of some big MD runs that were done recently by some people in the room here to give you a sense of what is possible now and what is still not possible. And then I'll spend some time on something that's closer to my own, that's exactly in my own research interest, on how can we use these machines to reach longer timescales. And then I'll finish with a discussion of what are the challenges that lay ahead in terms of using these machines to do molecular dynamics. Okay. So ideally, what we want out of an exascale machine is that when you get more computing power, you get more science out of it, right? So ideally, in the simulation space that's relevant for MD, so size of the simulation, accuracy, time, there is some kind of surface that bounds the amount of compute you have available, and you're kind of bounded by that envelope. And what we want is that if somebody gives you a bigger computer, that uniformly that space gets bigger, and then the science tells you where in that, under that surface here is the optimal place to be for your science. Right? And perhaps unsurprisingly, the take-home message of this is that it's not so easy, right? So some things will be easy to do on big machines, some things are hard to do. And there are consequences of this in terms of the science that we can be expected to do on these machines. But in a perfect world, that's something like this we would get, right? Okay, so I'll start and discuss these axes one by one. And I'll start with talking about scale and using runs that Aidan and Raul and Evan that spoke this morning contributed to. And I'll start briefly talking about the potential that was used and the challenges in having this run efficiently on GPUs. And then I'll talk more about the parallel scaling of these kinds of things in the weak and the strong sense that you heard a lot about this week. Then I'll switch gears to the timescale problem of MD, so the second axis of this simulation space. And I'll talk about a method that we've been developing for a number of years and that is especially well suited for these very large parallel machines. And finally, I'll talk a bit about accuracy. So I won't discuss the physics of these potentials, but try to discuss how the accuracy, the interaction between the accuracy of the simulation and the kind of hardware we have limit the kind of science that we can do with these computers. Okay, so the first part of a case study, that was a paper submitted at Supercomputing by a number of people in the room. So Aidan is somewhere here, right there. You heard Evan speak this morning, and Raul is also here today. Okay, so that's the abstract. Don't try to read it. I'll highlight the keywords here. So we're talking about big molecular dynamics simulations, where big means in the billions of atoms, using the snap potential that Aidan and his group developed in Sandia. So what we're talking about here are massive jobs, and this was done on Summit. So at the time, Summit was the biggest machine in the world. So it's still a really beefy machine. So big GPU machine running a big system on the whole machine and reaching simulation times of somewhere in the nanoseconds. So we're squarely in the big and the short type of regime. And the beauty of this work was that they achieved really incredible performance, so really, really high parallel efficiency on the machine, and also very high fraction of the peak computing power of the machine. And if you're not impressed by that number, you should, right? Because typically, the only thing that comes close to peak on these machines is doing linear algebra, the multiplying matrices. That's where you get very close to peak. But to do things that are non-trivial, like I hope to convey, that's quite an achievement. But what I also convey is that they had to sweat blood to get there, right? So you don't get this for free. Oh, okay. So I won't talk about the physics too much, but the potential that they used was the snap potential that that I don't use. And this is part of a kind of new generation of potentials that are out there that are based on machine learning ideas, in the sense that traditionally people would try to think hard about the physics and extract the physics into a few very well-chosen basis functions, and then I have a few knobs to turn to adjust the potentials to reproduce, let's say, DFT calculations. So the new paradigm, and it took us kind of a long time to get there, is that we realized that we're not that good at putting physics in these models. So we're just going to throw a huge number of basis functions at the problems and have lots of free parameters, and then just throw more data at it to get a good representation of the physics. So in the SNAP method, what you do is that you look at one atom and you expand the atomic density around it in some kind of Fourier basis, in quotes. So think spherical harmonics with some radial basis. And that gives you a vector that describes the local environment around an atom. But the problem with this guy over here is that it's not invariant to rotation, for example, which you know a real Hamiltonian should be. So you have to symmetrize it by doing some symmetry operations that are related, again, that are kind of common in spherical harmonics type of expansions. And it ends up corresponding to doing some linear algebra on these guys here. And then you say that the energy per atom in my system is some linear combination of these bispectrum components, which are themselves linear combinations of these coefficients up here. So the total energy is the sum of per atom chunks, and each per atom chunk is a linear combination of these bispectrum components. And then you get forces, which is the thing you really need to do MD by just taking the chain rule through that thing. But since these are kind of complicated beasts, then it ends up being a bit of a messy type of chain rule. Okay, so all of this is just basically designed to give you an estimate of the energy of the system that's very flexible, so you can have lots of these basis functions. And then what you need to do, MD, is to compute these guys over here. Okay, and so the philosophy here is that these are kind of expensive to compute, so you have base descriptors or basis functions that are very flexible and very expensive. And then you have a simple linear model on top of it. So there's other approaches, like Tim mentioned, where you have simpler descriptors here, but you pipe them into a big nonlinear thing, like a neural network, for example, where you would have more nonlinearity in the model here. So this is in the class of things where the model is simple, but the descriptors are complex. Okay, so this, of course, needs to execute on some machines, so you need to map this into a computer code. And so all these steps here map to something like a kernel, like we heard this morning, that compute these different things. But the key here is that all of these different tasks have very different complexities. So they're complex operations that are sometimes represented as very deeply nested loops that have funny indices and so on and so forth. So the whole thing to compute the forces here is made up of a bunch of pieces that each behave very differently from a computational point of view. Okay? So this is a fairly complex potential. If you're, don't know if you guys did the exercise of coding up an MD code for a pair or a three-body potential, but it ends up being way simpler than things like this. Right? You might have two loops that are nested into each other or something, but this goes quite deep under the hood. Okay, so that's a recurring theme, that modern potentials are fairly complex to just to formulate and also to implement on the machine, and that has consequences in terms of efficiency. Okay, so the first step, of course, is to take this potential and make it run quickly at small scales, and then you can build on this as a building block to do other things. And so, again, GPUs, all of these modern machines are GPU machines, except for the number 2 up here. So if you want good performance on any of these big machines, you need good GPU performance. And I think you're probably convinced by now, without understanding the details, that doing anything on a GPU is likely to be somewhat of an endeavor. And this is also true for the snap potential. And things that make it especially true is that you have many loops listed into one another. and that the looping structure is not regular. So it's not like you have just one giant dot product to do. It's very complex information that jump all over the place in memory. So things are complicated. So just going back in time, so this was the state of things before the Exascale computing project that you heard about started. And at the time, they had a GPU version of the snap code, and it was written by Christian Trott. So that name probably doesn't tell you anything, but you heard a lot about the Cocos framework in the last talk. So Christian is basically one of the first two people that started Cocos back in the day, okay? So if you had to choose anyone in the world to write the GPU code for you, then you probably would have picked Christian, okay? And so he wrote the first version of this in Cocos. And then at the time, that was the state of the art. And then an interesting exercise is to ask, okay, how well does this code perform on different architectures? So then you have different machines that came up as a function of time. And the key number to look at here is this normalized performance. Okay, so arbitrarily for this first machine here, this IBM machine, we decided that ratio was 1. Okay, and that ratio basically measures how many time steps you're getting out per second of the simulation, divided by the advertised computing power of that chip. Right? It says, okay, the vendor said the peak simulation rate or the big computation rate of the chip is this, and then that's how much you're getting out in terms of simulation, and then you can take a ratio. And then you compare other machines on the same code. So CPU machines do pretty well. In fact, these guys are above 1, so it means that they're doing even better in terms of fraction of peak that they're achieving compared to this guy here, and this is pretty good. And then you hit that line, and this is pretty depressing, right? It's roughly a factor 10 lower than this, and another factor of like 40 lower than this guy was. And if you go back, then unsurprisingly, this was a GPU. And then, oh, that's not too good. Then you go back to CPUs, things get better again. And then another generation of GPU, things get slightly better, but you're still doing noticeably worse than you were doing on CPU on this machine. Okay. So even though a GPU genius wrote this, this was still a case where, as a function of time, things didn't get better. And in fact, you could argue that performance was getting worse at fixed version of the code. So something had to be done because the success of our project, of our ECP project, was written as a function of the performance we could get out of the code, and we had a numerical target to hit. So if that trend kept going down, we were going to fail. Right? So we had strong incentive to do something about it. So I think Raul will talk about some of this today, but the purpose of this slide is that doing something about it is not easy, and it's not one thing either. Right? So this is a laundry list of things that they did to speed up the code. And there's a gazillion different things. And some things Tim mentioned, such as the memory layout, the array of structures of array, array of structs of array. And something that they found is that there's no optimal memory layout for everything. Right? So it was even better to change on the fly the memory layout as you run than to pick one and execute all of the kernels with it. Other things were things where intuitively you wouldn't think that it matters, but rewriting loops differently and breaking apart the kernels into different pieces helped a lot because you could tune the execution of all of these things independently. It used less registers, which are these kind of cache memory that's very precious on GPUs. But it also makes your code pretty messy. And what makes it even more complicated is that seeing this, you might think that the smaller the kernels, the better. But of course, it's not true. At some point, you can overdo it, and things go bad. Right? So there's really a huge space of optimization that you might think of doing. And it's really not clear which one of them is going to work or not. And so you just have to try it. And other things really come from the basic physics understanding, right? So there's a bunch of different ways that you can rewrite all of these nested loops, and computationally, not all of them perform equally. So I think it was Nick Lubbers that came up with this. He was staring at this, and then he figured out that this actually looked very similar to people that were doing automatic differentiation that need to automatically write gradients to big expressions, that these guys found more clever ways of backpropagating to this. And that suggested a new way of rewriting the same mathematical equations that had very different computational behaviors. Right? So again, there's nothing, these are mathematically equivalent expressions, but just the way that you decide to write this into different pieces. For example, you see here that the force calculation ended up dramatically simpler in this new view of the world than the old view of the world. Storage was better, fewer flops, and that helped a lot. Okay. And all of these things that I highlight here are all memory kind of optimization. Right? So how do you store things? How do you flatten arrays? And so on and so forth. And at the end of the day, starting from the first version of the code, you basically see that there's no one optimization that just changed the world. It's an accumulation of tiny, small things over a long, long, long period of time that just made the code go faster and faster. So at the end of the day, we have a plot like this from the beginning of the project to fairly recently, where you see the performance of the code as a function of time. So this is fixed hardware, and the different lines are different GPUs, and the line shows you the simulation throughput of the code as a function of time. And you can see a very spectacular increase in performance that over this period of 4 years, the performance went up by a factor of 26 in that case. So it's exactly the same problem, same hardware, and it took that long for a bunch of brilliant guys to bringing up to that speed. So then, of course, the final Exascale machine was not the one that we had all along to work with. It was a new architecture that came out of thin air, and then we had to see whether the code was still working well there. And at first sight, you think, oh, well, that's good, right? If you look at these lines, they all went up on the new architectures, just like they went up on the old architectures. But if you go back and you see at what's the advertised flop rate of this thing, then you see that magically we're doing like 3 times as poorly on this architecture than we are on this architecture. So again, details really matter. Exactly what the vendors decide to put on the GPU, how big the caches are, all of these things end up being important at the end. So the details don't really matter here, but I think that's a message that Evan mentioned before, is that if you buy a piece of hardware and you just read the sticker and it says, oh, that many teraflops, that doesn't mean that that's what you're going to get if you actually run something on it. Okay. So the slightly depressing thing that came out of this is that if you follow the literature on these ML potentials, there's basically one new ML potential coming out every week where somebody comes up and says, oh, look at my brand new way of doing this thing. Everybody has their flavor of the month of this thing. But now if you start asking, it took these guys 4 years to get this up and running to something that really approaches what the hardware can do, then it kind of tells you that there's no way that as a community we're going to be able to invest enough effort that a significant fraction of all of these potentials that people promise would run efficiently on these machines. Right? So something is going to need to happen. We're either going to need to converge on a subset, or we're going to need to learn to do this kind of optimization much faster than we know how to do them now. But so it's exciting that people are just proposing new ML all the time, but in the long run, it's not sustainable given how hard it is to implement these on the modern machines. Okay. So now I'll kind of switch gears, and I think today with Evan talking, we focused a lot on the very low-level optimization. But I think as a program here, we're not GPU coders, and we don't expect that all of you guys would become crack GPU coders. And so what we're more interested in, I think, as a community, is to first think about higher-level algorithms of how we can exploit these machines, but keeping in mind that they will need to run at some point on an efficient machine. And then once our ideas are fleshed up, and now we can reach out to experts like Evan and Rahul to help us. And the hackathon is kind of here for that, right? That we can really reach out to people that know how to do this, and we can focus on higher level concepts. But the key, of course, is that you have to keep the complexity in mind, because otherwise you're going to get to an endpoint that's impossible to program on these machines, and that wouldn't be an outcome that we want. So I'll start talking more about, now that you have this base capability where you can compute things, what else can you do on top of this? So of course, the first thing that you can do is to just parallelize your MD, going from one GPU to many GPUs. And the expensive part of this calculation is to compute the forces acting on your atoms. This is just the gradient of your total energy of the system. And the way this is done now, like in LAMPS, for example, is by domain decomposition. So if I have a big system, I partition it into a bunch of subdomains. And each GPU or core owns a subdomain in the system, and they're in charge of computing the atoms in their own subdomain. But the trick part, of course, is that if I want the force on this guy, it will depend on the position of atoms in different subdomains. So at every time step, you're going to have to exchange your boundary positions back and forth between all of these domains. So this is fine if you have a lot of work to do internally compared to how much it costs to talk to your neighbors. So as long as you have way more computation than communication, you can arrange your code so that you're hiding communication under the hood. So this is what people exploit in these big runs, and this is why MD weak scales. So again, weak scaling means that the size of your problem grows with the number of processors that you're using to solve it. Okay, so if I'm happy with this setup, and for Christmas I get a machine that's twice as big, then if I make my system twice as big, nothing changed, right? I'm running at the same efficiency as I was before, and you just can keep coasting on this forever, right? And basically, if you look back 20 years, that's roughly what we were able to do, right? Just push the system sizes, and almost for free, you would get bigger systems on new machines. So this is nice, right? Maybe it's not free lunch, but it kind of approaches the free lunch limit where once you did the hard work of writing a good parallel MD code, it's likely that you're going to get good mileage out of it.
Okay. Next question.
Yeah.
Do you anticipate any value in like non-uniformly breaking up decomposition? So putting this few processes where you anticipate lots of communication and less processes where you maybe not expect it, or the way that value would be less.
So there are a few approaches out there when they do this. I think the guys in Ulick are looking at that. And I think it depends a lot on what your system looks like, right? If it's kind of homogeneous in terms of mass distribution, it's probably not much to gain in being really clever with your domains. But if you're doing systems with big pores or really heterogeneous mass distribution, then there are ways to arrange, to load balance the domains so that they all spend roughly the same amount of time. Because in these approaches, they have to move in lockstep, right? So if one domain goes slow because it has more atoms, it slows down everyone. But yeah, that's something that in principle, it could be useful depending on the problem you're doing.
Yeah, I was thinking with those, like a helium bubble, right? You could have, and there's definitely an area where the action will be larger within the bubble, and you'll have a lot of areas around that. The atoms will move relatively slowly, right? So where you can exploit the fact that then they won't be moving between processes.
Yeah. So do you move atoms between processors as soon as they cross the boundary, or you buffer them for a while? Yeah.
Every time the neighbor list is rebuilt, which might be like every 20 time steps or something, then atoms get exchanged. But there is stuff in LAMPS as well that I haven't, it's a little bit tricky to make it work efficiently, but if you have empty space, you can turn on load balancing and it'll assign the big void to one processor essentially and try to rearrange all of these boundaries. There's a few different algorithms, some are more complicated than others. You can rearrange the boundaries so that every processor has roughly the same amount of work.
Mm-hmm. Yeah. Did that answer your question? Okay. Good. So a demonstration of that, going back to my earlier case study, is that they did a weak scaling study, so the number of atoms per node is constant, and you just crank up how many nodes that you're using on the machine. And basically, ideal behavior will be a straight line here. So this is number of million atom time step per second, but per node. Okay, so if you were at constant performance and you would just get 10 times faster when you have 10 times more node, this would just be a flat line. And you see that is roughly what you're getting, right? If you have enough atoms per node, you can fill an exascale machine, no problem, and you can do these giant simulations. And of course, the key word is enough, right? So you need a sizable number of atoms per node in order to get this weak scaling. So when you get to strong scaling, things get a bit dicier. So strong scaling is you keep your problem size fixed and you increase the number of nodes. So this is time to solution. So how many seconds it takes to take one time step. And ideal performance will be a 1 over number of node line, right? So if you have a ton of atoms in your system, then you're basically perfect strong scaling. And then when you start having not enough atom in the system, then you just level out, where more resources don't buy you anything, and you just cap out at some simulation rate. And here is the same thing, but in terms of throughput, ideal is the same constant line. Big systems, no problem, you can fill the whole machine, but small systems, you see that the performance starts dropping compared to the peak as you start pushing this up. And again, big or small is relative, right? Many of us billion atom, we wouldn't call this a small system, but at these scales, these are small systems. And this is even more true when you take into account the fact that Snap is not a cheap potential. And I'll come back to this at the end. So for small systems, strong scaling breaks down, and that means that you max out at some simulation rate. That's something like 10 nanoseconds per day, no matter how much compute you throw at the problem. And for people that have been doing MD for a long time, this kind of nanosecond per day type of number is something that we would get on classical MD on small systems for a long, long time, right? So this basically lets you go at the rate that you were going on an old empirical potential, but now you're going at that rate on these modern machine learning potentials, which is good, but it's still basically leveling off wherever we were leveling off 10 years ago. And this is, of course, because of communication, right? So this is a breakdown of where the time is spent in these calculations as a function of size. If the system is big, in pink here is the fraction of time you spend computing the forces, and it's essentially 95% of the time. And once you start having fewer atoms in the system, crammed on the same number of nodes, then the communication cost just starts skyrocketing, and that's the thing that kills you. And this is because when your domain size becomes smaller, you have fewer and fewer atoms in the domain, so it takes less time to do this, but communicating with your neighbors, there's a latency associated to this. So you have to pay a fixed cost to talk to anyone, even if you don't send any data. And at some point, that just kills you, and you spend most of your time just waiting for communications from elsewhere. And I think that's a cool illustration that this, in red, is really the cost of computing the forces. In green is the cost of doing the communication. And everything else is this tiny sliver here. Like, so time stepping, the equation of motion, doing the analysis, everything is just in here, right? So in a regime where things are performing well, you really spend all of your time computing forces. And that's a nice thing from a computational point of view, because the thing you have to obsess about is to compute the forces. Right? So you don't have to obsess about 10 different things that have to be optimized. There's really one thing that stands out that you have to beat on really, really hard. Okay. So the bad news here is that bigger computers don't buy you longer simulation times. We could get at these simulation times a long time ago, maybe at slightly lower accuracies, but really nothing dramatic changed in terms of time scale by getting these machines. So that's a cartoon of a nominal potential in the simulation space. That's what you could do. So in terms of timescales and number of atoms, in principle, everything under the dotted line here, you have enough computing to do, right? But communication costs is trimming a big chunk of that space. So what's left is this small time, very large systems. And as the computers get bigger and bigger, then that simulation space increases. So the technology is pushing us this way. But if you go and do a Google Scholar search of what people are running MD on, you'll see that we're basically all bunched up over here, right? We're all trying to do more nanoseconds on something like sub-million atom systems, and probably 95% of us are over here. And there's good reasons for this, because there's a lot of science that happens at these relevant timescales over here. So that is why there's a lot of scientific pressure in pushing to these longer timescales. So of course, Tim is really happy living all the way up here. For extreme things like big shocks, large frictions, things blowing up, that's where you want to be. But where I want to be is here, and things don't look so sweet for me. Okay. So what can we do about this? And the more depressing thing, I think, is that this says that if we get a bigger machine, Tim gets happier. If I get a bigger machine, I just get more depressed because nothing changed. Okay, I'm just wasting more power, and I'm not doing more science. Okay, so how can we rethink our whole algorithms to reach longer timescales? So parallelizing over space is out. What I want is to parallelize 10,000 atom, 100,000 atom, something, but just push this to very long timescale. So since we cannot parallelize over space, we're going to have to parallelize over something else, and the only thing left is time. So before I go there, you might ask, why am I so obsessed with long timescales? Why couldn't I be happy just living here like everyone and just go on with my life? And this is because for a lot of processes and materials, there's a huge separation of timescale between vibrations of the atoms in the system and interesting things that I find interesting, like defect nucleating, diffusing, interacting with one another. And that separation of timescale is huge, right? It can be thousands, millions, billions. So this movie here, you probably didn't see it because it's a bit hard to see, but it basically shows a surface. There's one atom on top, and then after a while, it just diffused and started moving around. So I'll put this in the bin of an interesting thing happening in the system compared to just vibrating atoms. But if that movie was to scale, we would have watched this for 6 months of atoms vibrating and not doing anything. And then for 1 second, something interesting would have happened. And then it would start vibrating again forever. So we spend a lot of time doing these simulations. And if you don't push them long enough in time, you really don't learn anything about the long-time behavior. You're just seeing boring short-time stuff over and over. And that doesn't tell you how your material would behave if you were to leave it out in the real world for a long time. Okay, so this is the thing that makes it very hard for us as MD people, but it's also going to be the saving grace. So this separation of timescale is what we're going to exploit to dig ourselves out of this hole. Okay, so just to restate what I said a bit more formally, so think of this as an energy landscape. So this is potential energy of the system as a function of configuration space axes. So if you plot an MD run on a plot like this, if it's a solid at low temperature, you'll see that all that you're doing, you're just vibrating around one of these minimas here, right? So the force is minus the gradient of the potential, so it's pushing you down towards the bottom, so you're just vibrating around. And you're vibrating at something like a phonon frequency, so think about roughly a picosecond type time scale for these vibrations. So that limits the time step of your time stepper to somewhere in the femtosecond time ballpark. And the thing that's useful that's kind of trivial, but that's useful to remind ourselves is that you're stuck with that time step even if the simulation is doing nothing interesting. Right? Just atoms vibrating around is what limits your time step to 1 femtosecond. And if you try to crank this up, it will just blow up. Right? It's not going to go. Initially, it's going to get gradually worse, but at some point, there's just no way to have a stable simulation. But the interesting things are things like jumping from one of these basins to another basin, and that might be a defect nucleating, reacting with something else, or annihilating, or something like that. And the rate at which, or the time you have to wait before this happens, is exponentially longer than the vibration time. And in the exponential is the ratio of the barrier that you have to overcome over the thermal energy. So if your barriers are much larger than KT, then the things you care about are much, much longer than the vibrational timescales, but these are the timescales that control your time step, and now you're kind of doomed, right? You spend a long time here, but where you want to be is here. Okay, so in that regime, what you care about is not exactly how things vibrate around, it's how much time am I gonna spend over here before I jump over here and something interesting happens, okay? So what we care about is what I'm gonna call the state-to-state trajectory, right? So how long did I stay here and where did I jump to when I decided to leave is what I care about. And exactly how boring things were in the meantime is not something that I care about. Okay? And this is what we're basically gonna exploit to speed things up. So the mental picture of what we want to do to parallelize over time is something like this, right? I couldn't take one of these simulations and scale it up to a big machine. So I'm just gonna have a large number of these simulations and run them all at the same time. And I'm gonna do this in a special way that lets me, after the fact, stitch these pieces together into a single trajectory that has the exact same statistics that what I would have got by just running one of these guys 3 times as long. Okay? So if I preserve the statistical property of my stitch thing, then I won. But of course, if I come with a magnifying glass and I look over here, I'll see that when I stitched these two together, they didn't perfectly overlap in phase space, right? That's astronomically unlikely. But these weird jumps are done in a way that it doesn't affect where I'm gonna go next and how long I'm gonna wait before I go there. Okay, so here my goal is to use many, many replicas of the system to generate the next interesting thing that's going to happen. And this is a solution to the strong scaling problem that I mentioned if these 3 things are true. Right? So if I can manage to run all of these guys independently from one another without talking to each other, then I can scale. Of course, I want this to be accurate at the end of the day. I don't want to generate garbage rapidly. I want really to be able to map this back to the real dynamics. And finally, I want to be able to use all of the pieces that I generated when I was generating these short trajectories here. Okay, so I'll just do a quick aside that these ideas are pretty old. It's kind of a new version of old ideas that were derived by Art Voter almost in '98, I guess, a long time ago, that he introduced these ideas. And Art is a chemist, and that was really derived the way physicists and chemists derive things, right? In a way that I was fully content with this, and I thought, wow, this is bulletproof. But then when you sit down with mathematicians and you tell them how bulletproof that is, it turns out that they're not convinced by what you're telling them. So we had that experience here at IPAM maybe, 13 years ago with Mitch, Tony, and Claude. And that turned out to be a really good thing that they were hard to convince because they really went up and really, really systematized and refined our understanding of how these methods work and of what is the error that we're making when we're using these methods. So that kind of launched, I think all of us are still working together on these questions now. So something like IPAM where you can try to do a sales pitch to someone and then they don't buy it, that can actually lead to a lifelong effort to make things more rigorous. And so that is the result of that kind of analysis. Okay. So am I doing? Okay. So what I told you about is what I care about is the state-to-state dynamics. Okay. So if I'm in some region of my configuration space, what I care about is when am I going to leave from this place and from which border of my domain am I going to leave whenever I'm going to leave, right? Because if I leave this way, it will be one reaction. If I leave that way, it will be something different happening. So I want to get that right. So the key concept that underpins all of this is the concept of a quasi-stationary distribution. And it is the limiting distribution that if I start a bunch of guys over here, I run them for a long time, conditional on none of them having escaped my domain for a long time, this is the limiting distribution that I get, okay? So it's a bit like an equilibrium distribution, but there's a conditioning of not having left my domain for a long amount of time in the past. Okay? So what you should mentally picture is that maybe I have a swarm of simulations starting here, somewhere in my state, and then I'm going to put absorbing boundary conditions at the boundaries of my state. And as I start running this, the distribution function of these guys will evolve. And at some point, it will converge to some stationary distribution, which is quasi-stationary in this case, because I have absorbing boundaries here. Right? So I'm leaking probability all the time. So people are leaving, they're getting killed, and then I just renormalize the distribution to 1. And at some point, the shape just converges to something that doesn't change anymore, right? So that limit exists, and that limit is what we call the quasi-stationary distribution. So why am I telling you about this? Well, it turns out that this distribution has very interesting properties. I'm going to go back here. That you can show that that distribution is unique. So no matter where I start in the state, I'm going to converge to the same quasi-stationary distribution, just like equilibrium, right? However I initialize my system, at some point I'm going to reach the same Boltzmann distribution. So this is the same concept here. And the other key is that you converge to this distribution exponentially fast with a rate that you can't formally write down. And this is related to this, what we call the spectral gap of the generator of the dynamics. So basically, this is the rate at which you're going to leave the state. And this is something like the relaxation rate inside of the state. So you might need to vibrationally relax inside of your state, or maybe there's some tiny barriers inside of the state that you have to overcome. So this guide tells you how quickly would you overcome these internal type of relaxation processes. Okay, so no matter where you start, you get there, and you get there pretty fast, which is good. And once you're there, and this is where the money is, there's two properties that you can formally show. Yeah.
I just want to say, Danny, like, when you say exponentially fast and pretty fast, it doesn't quite describe it correctly, I don't think, right? I mean, you can certainly pick a basin where you have arbitrarily long time scales within the basin.
That's right. So if I do a dumb choice of a basin, then this guy will be very close to this guy. So I'm still going to approach it exponentially fast, but with a tiny exponent, right? That's right. Yeah. But it could be worse, right? There's no reason that it would be exponential in that thing. But not that there's no reason, but you could imagine a world where it's not exponential. And for some dynamics, it's probably not exponential. And this would be a case where you would be in a bad shape no matter what. Right?
But all it takes is one barrier in your, what you think of as one state, to make it as slow, basically, as to
yeah. Totally right.
But even if there's a small difference between those lambda 2 and lambda 1, even a small difference will give you a pretty fast convergence rate, right?
Well, not really, right? If this approaches this, then you have an e to the 0. I mean, so you're not decaying with time very fast. Right? So it would be e to the this times t. That would be your decay to equilibrium. So if I pretend that I'm a mathematician for a second, this statement, the beauty of this is that it is true no matter what state, right? You can prove exponential convergence no matter how I draw my boundaries. But of course, in practice, if I'm just a toddler and I draw some random state with some garbage gap, then it's not useful, right? It's mathematically true, but it's not something that you can get speed up out of. Okay, so yeah. So this is kind of, you can think of this as a rate at which your system forgets about where it came from in the past. And if that rate is large, then things are going to be nice for you. If that rate is tiny, then you will, intuitively, you figure out that it will be hard to parallelize in time if the system keeps remembering where it came from in the past. But the key properties are these two things, right? That once you reach the QSD, the first escape time out of that set is an exponential random variable with a rate that corresponds to this eigenvalue here. And the first escape point is also a random variable that's uncorrelated with the escape time. So if you go back to your statistics class, you're going to see that this is basically the definition of a Markov process, right? The rate where it goes is independent of when it goes. And it goes at a rate that is, well, the random variable for the amount of time you're going to spend in a state is exponential with this rate. So the beauty is that once you get to the QSD, whatever happens in the future doesn't depend on what happened in the past, right? So if I stay in my state for a time that's longer than the inverse of this, I completely forgot where I came from. So now this is starting to smell like something where I can use this to parallelize, right? If I kept being correlated with the past, then it would be hard to run independent trajectory and stitch them together. So this is really the key. So what this says is that if I have a trajectory that just enters in a new state, and I stop it right there, and I ask, what's the distribution function for where and when I'm going to get out of this? It's a mess, right? It's a really complicated function of where I enter the boundary, with what momentum I enter the boundary, and it's messy. But now if I look at this guy, and it spends a long time in that state without leaving, and now I ask the same question, where is it going to go out, and when is it going to go out? Then it turns out that it doesn't matter anymore how it entered there, right? It completely forgot where it came from. So the next escape becomes a Markovian process. And this is really the meat of the statement, is that any trajectory that spent a long time in a state without leaving is completely statistically equivalent to any other trajectory that also spent a long time here without leaving, with respect to predicting when and when it's going to leave, right? So since the QSD is unique, I have two of them, they lost themselves, they reach the QSD, it's the same QSD, right? So where and when they're going to leave after doesn't depend on how I initialize the simulation at the very beginning. So they're all going to leave in the statistical sense with the same probabilities. So now this gives me a building block to do the stitching that I was telling you about, right? So the key time scale here is this inverse of the spectral gap. If I spend a time that's long compared to this in a state without leaving, I forgot where I came from, and now I'm a member of an ensemble of equivalent. I can prepare a bunch of equivalent trajectory in that state that are all the same with respect to predicting the future. So to generate trajectories like this, it's quite easy, right? You just start running MD, you don't do anything special, but you just monitor when's the last time that you left a state, or that you just started your trajectory from scratch. And if that time is longer than some correlation time that obeys the condition that I mentioned in the other slide, then you can start the official clock. Now you can start staring at your trajectory. And if it makes a transition, now I'm not allowed to cut it here. I have to keep it going forward until it spends long enough without leaving. And now I'm allowed to stitch. I'm allowed to end my trajectory, right? So this is a completely unbiased MD trajectory, but I just trim it down so that it obeys these conditions, that it stayed long enough in the same state at the beginning, and it stayed long enough in the same state at the end without leaving. And if I prepare a bunch of trajectories like this, independently from one another, I can generate a correct state-to-state trajectory by just splicing these guys end-to-end on a discrete state basis. And I'll get the right statistics up to an error that's exponentially small in whatever value of TC that I choose. Okay, so I choose TC. I can always make it big enough that the error I'm making is small. And then I can generate segments according to the recipe I just gave you. Yeah, the problem I'm glossing over, of course, is that you can formally write what these eigenvalues are, but in practice, there's no way to compute them, right? So you need a good way to choose this correlation time so that you're not making errors that you don't know that you're making. But there are situations where we know how to do this, so I won't spend too much time on this. Okay, so this gives us the ingredients we need for strong scaling, right? The first ingredient was that they have to be independent from one another because I don't want to spend my time communicating. So we checked that box. And the second one was accuracy. We also checked that box. We have a knob to control this, so we're in good shape. So this algorithm is what we call parallel trajectory splicing, or parsplice. And it's basically exactly the cartoon that I showed you in the beginning, except that now you should understand these guys as being prepared by the special procedure that I just told you about. And then I can stitch things together and go on my merry way and generate a long trajectory that has exactly the right statistics. Okay, so this is good. So what can go wrong, right? So my third bullet was that I need to be able to use all of the small pieces of trajectory that I generated, right? Because if I pay for a trajectory and never use it, then it's just waste, and that hurts my scaling. So something that can happen here is that I start a bunch of guys, and the first guy leaves to state 2. And now, to move forward, I need something to tie to the end of state 2 over here. And now I have a bunch of guys here sitting in state 1 that I have nothing to do. So you could be sad and just say, well, too bad. I'm just going to throw these away, and it's the cost of doing business. But since you paid for them already, you might as well just keep it on the shelf somewhere. And if my trajectory comes back to state 1 in the future, then here you go. I have something in state 1, I can consume it, and now I'm in state 3. I didn't need to run any more MD. So you might think that it's a bit of wishful thinking that in an astronomically large configuration space for real systems, and I'm going to land back in exactly the same state again in the future. But in reality, it's not that rare, right? These kind of what we call superstates or superbasins are all over the place. And they're basically exactly that cartoon here. Groups of states that are tied together by low barriers, but that have high barriers to go somewhere else. And these are everywhere. So some of them are tiny, 4 states. Some of them are 1,000 states big. But it is very common. They're not always there, of course. If you melt your system, now you're lost in the sea of infinite number of disordered states. But they're a fairly common occurrence. So anyway, you paid for the trajectory already. You might as well keep it in case that thing happens. OK, so this kind of trick is something that is pretty common, where you do some caching of things that you did, or you pre-compute things. But here we make decisions on the fly, but sometimes even the best decisions don't pan out, and you over-generate MD simulations in some state. But this caching gives you a way to potentially amortize your costs in the future. OK, but even better would be to not make the mistake of generating too many segments in some state. So let's do a thought experiment that I have an oracle that tells me the future exactly. Right? I know exactly where my trajectory is going to go. So in that case, I can start the exact right number of segments in each state, and I can splice everything, and I have no leftovers, and I'm happy. But of course, if I had an oracle like this, I wouldn't need to do the run to begin with. But it's a thought experiment that's telling you that the optimal thing to do is probably not to put all of your eggs in the same basket and run in one, but do something more clever. So if you don't have an oracle, the second best thing to do is to approximate an oracle with a statistical model. So what we do in the real code is that we learn on the fly a model of how the states are connected, and then we do simulations on that model to predict the future of the trajectory, to decide how many of these segments should I start in each one of these states. So I won't say too much about this, because I'm going to tell you more about our recent work on that in workshop 1. But so these are ideas that we're building on. But the beauty here is that if my model is bad or wrong or just naive in some way, it will just affect my parallel efficiency. It won't corrupt the dynamics that I'm generating. Worst thing that can happen is that I generate too much here and not enough here, and I would just have to go back and generate more in order to make progress. Right? So these errors don't contaminate the rest of your simulation. They just affect your speed up. OK. So these kinds of speculation ideas, I think, are pretty cute. And if you look in computer science, they're actually fairly common, very low level, close to the metal. Right? The compiler does a lot of speculation at the branch level. But here we're doing speculation at a very high level of the tasks, of what I'm deciding to run in the system in order to make the efficiency. OK. So how does this work in reality? So I'll show you results that we got with Rao Wang, who visited Los Alamos a couple of years ago. And we basically did some parse splice on a bunch of nanoparticles. We did a lot of runs. You don't have to try to read this, but we're able to reach very long time scales on very complex systems. So these are things where there's millions of different states, hundreds of millions of transitions along the way. And what we see is that if you do something easy, like a low temperature system, where all the transitions are rare, then you can scale the hell out of this, and you get great performance. So this number basically tells you how many segments how many batches of segment of all your processors do you need to consume to make one jump out of the state? So that says that I could keep everyone busy for one segment, and I would generate about what I need to get out once. And in this case, I got amazing performance, so like 99% efficiency of splicing. And we were able to go at simulation rates of something like 10 milliseconds a day on that system, which is pretty good. Okay, but that's kind of easy, right? It's a system just like the cartoon I had at the beginning, where you really stare at this for a long, long time. Nothing happens, then something happens. So it's kind of nice that we're able to do it, but it's not especially impressive. So to make my life harder, I can just start raising the temperature, and now things will speed up, right? Things will happen more and more frequently. So I can pick a temperature here, 600K, and this basically says that I can use less than 1/1000th of a batch to do one escape, right? So here you should start being worried that I'm wasting potentially 99.99% of my effort, because the first guy is going to escape, and I'm just going to waste everything else. But they were, on average, something like 4,000 revisits to states in that system. So we could amortize all of this work and still run at something like 75% efficiency, which is pretty good. But of course, you can break this, and you just keep raising the temperature. Events are going to happen faster and faster. You're not going to revisit the same thing ever. So here was 6 revisits per state. You basically need one segment to get out. And then your simulation rate just goes back to pure MD, right? If you never revisit any state, if nothing is rare, and the best you can do is just do MD, and then you cannot scale at all. Okay. What am I doing? Yeah, 15 more? Yes.
Keep it, it doesn't quite reduce to MD, right? Because if you escape very quickly, you don't waste all the time of all the processors. Well, no.
No.
No, it's not right.
So, I mean, especially for a power splice, if the temperature is large enough, also, you're never going to manage to close a segment. Right? You're going to make transitions over and over. Your segment is going to get very long, and it's going to reduce to just doing MD forever. Yeah. Okay, and in this case, the speculation gave us something like a 4x improvement for hard cases, right? When putting all your eggs in the same basket doesn't work, speculation can really help. So when things get dicey, you really need all of these ingredients together in order to get performance. Okay, I'm not sure. I'll go quick on this. But at the end of the day, efficiency of these methods rely on the fact that something is slow somewhere, right? You're getting acceleration because there was a slow component of the dynamics. If the dynamics is super fast, there's no way to speed it up. So one concern you might have is that if I take a system like the cartoon I showed you before, and maybe every 4 picoseconds, some atom jumps, and now I make a system that's 4 times as big, now every picosecond something will jump, right? And if I keep making my system smaller, something will happen somewhere all the time. And you would think that that would kill your acceleration completely. And if you run just a standard power splice that I told you, then it will likely kill you, right? At some point, we don't deal very well with large system sizes. But the thing that is that most systems, at least in the systems we care about, when there's a transition that happens, it just affects your system locally, right? It's not like the system is breaking into 2 pieces. It's just locally changing what is going on. So is there a way to exploit that locality to make power splice sensitive to the rate at which things happen locally instead of the rate at which things happen globally? And there are ways to do this by reintroducing these spatially parallel strategies. So I can take my big system, separate it into a bunch of subdomains again. And now I extract the subdomains, and I basically embed them in the right environment, right? So this guy would know what the neighbors look like so that it fits in the right environment that it's embedded in. But then I would run power splice on each subdomain by itself. right? So they would all run and generate segments locally. And then with a more sophisticated parse-splice machinery, you would try to propagate the whole system by splicing pieces everywhere until you can propagate the whole thing forward in time. And that's not super hard to do, but you have to deal with synchronization, right? Because if there's an event that happens here that kind of affects what this guy looks like, then I have to resynchronize this guy because he has to know that the boundary changed. So you still have to talk to your neighbor, but you only need, I'll skip over this, you only need to talk to your neighbor when something happens. Right? If no events happen, I don't need to talk. So I don't need to talk at every time step, which is very useful. Okay. So how do I actually run this on a large-scale machine, right? It's kind of a tricky type of workflow. I have a lot of tasks. They're all pretty short. None of them scales very well, and the tasks are independent, right? What I choose to run next depends on what happened before, so I have to keep making decisions very, very fast. So I don't want to rely on Slurm to do this, and we had lots of discussion before. You don't want to rely on files to set your system up. And you don't want to synchronize everyone because you might have hundreds of thousands of guys that you don't want to synchronize. Okay? So you have to move to something where everybody lives in the same environment and can interact without files, and in a way that a lot of the machinery of communicating and doing I/O happens in the background while something else more interesting is going on. So the way we're doing this is with an infrastructure that we call Exalt, where ourselves we manage the data movement, the task movement, the task queuing, the task execution. We do all of this ourselves. So we basically ask for a giant allocation on the machine. Then we get all of the cores, and we set up this infrastructure that we use to manage all of our simulations. I'll go quick with this, but I'm happy to discuss if you have questions about it. So there's basically the brain of the whole operations that sits here, but he's not driving the show. What's driving the show are these guys here that are aware of the resources that are available and who's working and who's idle doing nothing. So basically, whenever there's a chance that in the near future some guy will become idle here, he tells the brain here, say, I'm going to have resources coming free, tell me what to do. And then this guy has to come up with new things to do, like go run in state 4, go run in state 23, go run this. And then in the background, I need a configurations to run in. That needs to be somewhere, and that lives in this database over here. So all of these dependencies, all of the data I need to do my simulation is actually moving in the background asynchronously over the network and assembled over here. And once the task is fully ready to run, it just sends it down to the first guy that's available. So this guy is buffering a bunch of things to do ahead of time. Every time somebody is free, he gets fed something new in form of a task to do and some data to act on. And then the engine down there executes, sends the results back. And then this guy can buffer things, package this into larger messages, and start stuffing stuff back into the database here, and send what the brain here needs to know to make the next decision back up. But the key is that all of this happens asynchronously while these guys are just churning. They're running, they're running, they're running. As soon as they're done, they get handed something else, and all of the data is moving without these guys knowing what's going on. I don't have time, I'll skip this. I'll skip this also. So we can deal with heterogeneous architectures. So for example, when we run on GPU machines, typically we'll have a bunch of replicas that use one GPU each, and then there's a lot of leftover cores. So we can lump all of these guys from a few nodes into one replica and then add it up here. So it's very flexible. But I will skip this. So we recently ran on Frontier, this first Exascale machine. And with this kind of hierarchical infrastructure, we were able to scale up to the chunk of the machine we had access to at the time, which was 75% of the machine. So we had about 1% of the resources dedicated to managing the data and the tasks and moving stuff around, and about 99% of the rest were just down here crunching MD with lamps. Okay, so yeah, so at the end of the day, that was a pretty cool run, and because we have so much parallelism exposed, so we have this domain decomposition that I talked about, you have a bunch of replicas on top of each domain, and you have multiple GPUs per domain, then you can relatively easily fill a big machine if you do this. Okay, so I'm going quick because I just want to finish this last point about accuracy. So we have these hugely powerful GPUs that are there, and we should be really happy about this, but it also comes with aspects that are not so great from the science point of view. Okay, so they're so powerful that you need to stuff a lot of work to do on one GPU if you want to saturate performance. So for a snap potential, things look okay, right? That to saturate a GPU, you might need 30,000 atoms or something like that, which is not an insane number. But that is a fairly expensive potential, right? So now if you say, okay, I have an A100 in my office, I want to run EAM on it, which some of you might know, it was mentioned a few times, it's very cheap empirical potential, and I think all of the old guys here grew up running EAM, right? It used to be the bread and butter of material science, everybody was doing EAM. And now to keep one GPU busy with EAM, you need 10 million atoms on the GPU to keep it busy. Okay. And that is not a good news. Well, if you're Tim, that's a great news. But if you're me, that is not a very good news. Because, as I said, about 90% of the community is not doing huge systems for a short amount of time. Okay? So with these expensive potentials, big machines are good, right? A very large MD run that fills the machine might be 1 billion atom or something. It's large, but it's not insanely large. And if I run parsplice on this, I might run 10,000 atoms on a replica, which is fine. And if I decide to run just 1,000 atoms on a replica, I'm down to 50% efficiency, which I can kind of live with, right? But now if I want to run really long time scales, so I'm moving to a cheap potential, now if you do parallel MD, you're going to need close to 1 trillion atoms to get the machine busy. Okay, so some people need trillions of atoms, but I would argue that there's not so many of us that need trillion atom simulations. But this is the really bad news for me, right? That if I need 30 million atoms per replica to do parsplice, I just told you that we don't scale well with size. So this don't look so good. And now if I say, okay, I'll just bite the bullet, I'll run my 1,000 atoms on this and pretend that everything is fine, I'm going to run at 1% efficiency on the machine. So this is bad, okay? A lot of what we've been doing for years with these kinds of simulation methods really don't map well to the hardware that we have. So something is going to need to happen, otherwise the science we'll do will really be strongly affected by the machines we have available. So there's ways around this, and there's some ideas that some people in our team starting to look at. And something that we might need to do is to start having an MD code that's not running one simulation, but that is running 1,000 systems at the same time, all packed up into one system, right? So you might have a weird kind of overlapping systems. They all live together in the same MD code, but they don't see each other in their respective neighbor lists. And then you can do like parsplice on one chip with 1,000 replicas all running on the one GPU, okay? But in principle, if you want to badly enough, you can go sit down and write a code like this. But I think we're going to need to think hard about this as a community and provide tools so that you and I and our students and anyone can really exploit these architectures to do good science. Okay, so coming back, wrapping up, the wish at the beginning was that bigger machine would just uniformly expand our capability to do cool science, and you're free to define what's cool for you, and the machine will help you do that. In reality, that's not what we get, right? We get big systems for free, we get super accurate systems for free, and we just get hammered in terms of time scales. And in many, many aspects, that becomes harder and harder for us. Right? So the machines are pushing us there, they're also largely pushing us there, and they're pushing us away from here, but I would argue that there's a ton of science here that needs to get done. So we're going to have to keep thinking about how we get better and better and develop algorithms to get there. And I think there won't be a good hardware solution here. It will be mostly a methodological solution in terms of extracting that information more efficiently than we are right now. Okay, so that's all I had. I don't want to end on a depressing note. Obviously, a large computer is better than a small computer, but it is not all nice and rosy. So we're going to have to do some work in order to get there, and especially to avoid being too constrained by technology in terms of what simulations we're running and what problems we're going after. Good. That's all I had. Happy to take any question.